speaking get started? Okay, cool. So welcome everybody. This is I believe our first visual computing visiting seminar speaker of the semester. I'm really glad to attend here to kick things off. So Yotam is a professor at Gingold University, hidden by our box, who does a bunch of really cool work in graphics, particularly spanning geometry processing, and a lot of interesting applications thinking about creativity, broadly speaking, including implications for HCI and perception, psychology, all those things put together. He's done a bunch of really cool stuff recently, which I think we're going to hear about. But thinking about color spaces geometrically and what you can do with that in terms of editing images, if you take that perspective. Some folks in the room have been around long enough to remember this, but most folks haven't. But Yotam did his undergrad here at Brown back in the day, the good old days, before going on to doing his PhD at NYU.
Good despite it.
Yeah. So lovely to have you. Take it away, man.
Thank you. Yeah, thank you. I wasn't originally going to come in person, and then my wife went away last weekend, and I thought, well, come on, if she can do that, then I can do it. I got a last minute. Here
you are.
It's really nice to be here. So thank you, for having me. Yeah, and I thought, okay, what am I going to talk about? Got a bunch of students. I do work in a bunch of different areas: design, sculpting, drawing, painting, sound, color, motion, scientific expression. I'll give people a grab bag. So before I go any further, this is actually a photo of me in the Sun Lab taken around 1999 or 2000. That's me in the corner. So I don't do this for every talk, but I do that for this talk. So now I have my own students, right? So these are my 5 current PhD students, and each student, gets their own topic area, right? So Sean and Jan, by the way, are on the job market, so you should hire them. And they do all this great work. I get to stand up here and tell you about their work. I'm going to tell you about 3 recent projects: one on color, one on shape, and one on thought. And so jumping in there to the first talk about color, this is work by Ted and some of our collaborators, but I'm basically talking about what Ted spent all of his time on. And Ted deserves all the credit here. And so the topic of this is palette-based editing, which came out in 2015. And specifically, we're going to look at a series of follow-up works on geometric palette-based editing. And in these works, we can look at the colors of an image in color space, and color space for humans is 3-dimensional. So here I've plotted a red, green, blue color space. And in this approach to geometric palette-based editing, what we can do is we can look at the pixels of the image, we can compute a convex hull, we can approximate that convex hull to reduce the number of vertices, and then we can say, all right, every vertex of that convex hull is a color in a palette. It's a sort of representative palette that we can use to plot every pixel in the image. So the pixels in the image are located inside of this palette. And so using work from geometry processing on generalized barycentric coordinates, we can find blending weights. So any color inside of this approximate convex hull can be written as a blend of the vertices. And we do that for the image. The image now becomes a weights times the palettes, very simple, efficient, parallelizable computation. And by changing the palette colors, we can change the image. And we can get these, smooth changes in the image. Now, when you do this formulation, lightness is actually very hard to control. So this is an example of just there's like a little delay through Zoom as this goes. The server is far away and comes back. When if you have like a linear gradients, right? So you have this ramp going from black to 4 different colors there, right? If I go and I change the palettes, the colors of 2 of these 2 colors in the palette, then we can get a different color, but we can't change that ramp. We can't change the way the color is changing in lightness. And that's something that people want to do. That's something that designers, photographers, they very much want to do this. This is the sort of the first thing that's new in this work I'm talking about. right now is letting you change the lightness, or the tone of the palette, the colors in the palette. And something to point out about these is that, these tone curves, they're not previous works, right? Like if you go from Photoshop or Lightroom, there are tools for editing tone curves, but they're global, right? They're global. So I can take this image and I can open the curves palette. I could adjust the tone curve. I can kind of make that gold, have more contrast, but I'm also going to be undesirably changing the contrast of part of the image there. So the figure there. And you could say, well, just mask it, right? Go and, create a nice mask. So I can create a nice mask, but this actually can be really tedious. So if I create a mask around the top, now I'm only editing the tone curve for the area on the top, but there's reflections all around the image of this, this gold color. And so I haven't edited those. So that's very tedious to do. And another problem with these palette-based editing tools is that if you want to just click on a pixel in the image, you don't want to use the palette, but you don't want to lose the palette, you just want to click on an image and change it, it's actually kind of unintuitive. So if we look in AV space, let's just look in a 2D color space here, so it's easier to visualize. If you have a 3-color palette, any color on the inside is a blend of these 3 colors. Great. Now, if I want to change that color, I can do it by changing the palette. There's the 3 versions of the triangle, but there's infinitely many solutions. Right? It could be this triangle. It could be this triangle. It could be this triangle. So, which triangle should it be, right? And looking at this in image space, this is like me going and saying, there's a pixel right here on this cup, and I want to change the color of this pixel. What should I do to my palette? So the high-level summary of the ColorfulCurves is that with palette-based editing, you get these nice spatially coherent color edits, but it's hard to control lightness. And it's incompatible with just directly changing a pixel color. On the other hand, tone curve editing makes it easy to control lightness, but you kind of need to manually mask your image in a very tedious way. So if we take these features that we like, we put them together, we get ColorfulCurves. Okay, so what are we doing here? So the first thing we'll do is let's use LED color space, because this is decoupling lightness from the colorfulness and the hue of the colors in the image. So now we've separated the still 3-dimensional color space because we're humans. But now, we've got our dimensions nicely separated. So the first thing we can do is look at AV space. So in AV space, the colors of the image, they're still, the lightness is constant. And we can still do the similar things we've done before with convex hulls. We can take an approximate simplified convex hull of our images. We'll always want to add an extra vertex in the center for gray, because gray is special. You don't want things which are gray to become colorful unintentionally. They're like perceptual meanings to some of these things. So we kind of always have this gray color, but we have a palette. Great. So we have our palette, but our palette now no longer talks about lightness, no longer talks about the lightness of anything. And we can do the same thing we've always done, but just in 2 dimensions, just for these 2 dimensions. So our palettes are now have 2-dimensional, AV space values. Whoops. Great. Now for every color in the palette, we can give it a lightness curve. And we'll start with just a linear function, just an identity function, right? So the lightness is nothing interesting happening here. But if we take these together, we can apply the lightness for every pixel, and go through this lightness, this lightness function to get like an output lightness value. And we do this with biharmonic functions, which I'll get into a little bit later at a high level. But the point here is that every palette color has its own lightness function. We can reuse those same weights. So those same weights get reused to combine the different lightness functions for the palette. So the same blend weights which we're using to blend the AB space colors, we're also going to use to blend these functions, the output of these function values, and that will be the output tone or lightness value for the pixels. Great. So we take all this, we put this together, and we have this nice formulation of our palette-based image editing. And this brings us to, okay, so I want to change this this color in this image. I can do it now in two ways. I can change its lightness by going to a picture, by going to the tone curve and kind of dragging it around. And I can change its colorfulness by changing the color that that palette maps to. Great. Now, if we're going to do this for somebody, if we're going to do this by letting people click on a pixel and edit that pixel value directly, then there is something else desirable. We know there's infinitely many solutions, so we would like to prefer the solution that's the sparsest change. And what that kind of means is that, like, if you could accomplish this change by changing every palette color a little bit, that's probably not as good as changing just one or two a moderate amount. It's like unpleasant to have just everything swimming out from under you. So that's sort of our goal is, it's going to be how to solve that. Okay, so how can we find the sparsest change that satisfies some constraints? All right, so we can express our sparsity with kind of this L21 norm. The L21 norm is going to measure how far colors are moving. In Euclidean distance and color space, but then the one there means we're taking the square root before we sum things, and so that means that we're kind of every color in that palette, we're measuring its difference separately rather than together, and it leads to a preferring to change fewer colors rather than more colors, all things being equal. We're also putting in the tone curves here, and there are biharmonic functions, and this is kind of, I'll say read the paper for details. And then we want to express the constraints that the user is placing. So the user's chosen a color, and they've said I want this red color to become this blue color, and so we have to express that in terms of the AB, so the colorfulness and the hue. And so that's another term that we can place. We can express this as a constraint just on the colorfulness. This is just saying that the color should be the desired color. And we can do a similar thing for the lightness. And we can say, however, when you combine the lightness for this pixel with the weights, we also want that lightness to give us the right desired values. Great, so these are just, three terms. Take these three terms, put them all together, plug in a, SciPy, optimize, optimize, minimize, put these things in there, and you get, something that, you add your constraints so you stay in gamut, so the colors aren't imaginary colors, and you get a 30-second solve, right? Which is like not very good for interactivity. That's like, definitely switch to a browser tab and get distracted for a long time, not interactivity. So can we do better? Yes, we can do better. We can realize that the two different kinds of degrees of freedom that we have, the colors of the palette and the lightness values, we can kind of separate them into two different blocks of coordinates. And when we do that, we realize that actually they're the lightness values, by expressing them in this as this like with this bilinear energy as with constraints, we can do this as like a fast linear solve. To get our updated luminance values. And then if we just look at the colors, there's not very many palette colors, and there's not many degrees of freedom there. Just AV for a small number of palette colors. So that we can leave as like a that becomes a small QP problem with quadratic constraints. linear constraints, right, quadratic energy with linear constraints, it becomes a small QE problem. And by alternating, solving one and then minimizing the other, and minimizing one and minimizing the other, and fixing them, we end up with something that runs very fast. 400 times faster, runs in real time, everybody's happy. And so just to give you some examples, here is a recorded demo. Right, well, we can click on the different palette colors and we can change their tones independently, right? Or we can, put out all these things together and say, let's do some constraint-driven, color editing. Let's go and let's, click on a spot in the image and say, okay, let's change this, let's change that color. Let's change its, AV and L values, and then, some of the palette colors are changing, and we're seeing which of the color palette entries have had their luminance values change. So that optimization changed those two, but didn't change the other, which is why we saw them move off with the identity.
So sorry, the Fs that are representing the curves, those are changing as well?
Exactly,
Okay.
exactly. So the optimization can say, well, the optimization will have to change those if the luminance of that pixel changed. Right, and that's, so then the optimizer is basically deciding, which of the colors, right? We got this convex shape around the pixel, so it's like, which of those vertices should it change the luminance of, right? And it decided that the smallest change was to change the reddish and bluish color.
Yes, so the examples you are showing these five vertices in the convex color. Does it have to have more or?
Oh, wait, why are there five?
Yeah.
In this case, yeah, I mean, it's a user tunable parameter, just like how many colors you
But in
want
practice, I mean, from the user point of view, does it have
to have more.
more degrees of freedom?
Yeah, I mean, it sort of becomes unwieldy if you have a lot,
Right.
So this is, so now we have, 2D convex hull palettes. In the previous work, we were always doing 3D palettes, right? And 3D palettes, like, the more you had, it can become very awkward to adjust them, right? You could have like 20 and have a better, like a tighter prox. Okay, so here's the trade-off, right? If your colors in color space they'll have a distinct shape. So the more vertices you have, the tighter the convex hull is around that shape, the less dead area. And that means that the weights end up being sparser in general. So some vertex will have like more control over some colors and other ones will fall off to zero faster, which is like usually a good thing. But then you have like 20 palette colors and that's like, you don't want that either. That's also, not good. So 6 is like a sweet spot there. Now that now that we have these 2D palettes, I don't know if we settled on a smaller number. I mean,
Feels like you should be able to get away with a smaller number.
Yeah, you just needed to wrap,
Yeah.
the 2D. Yeah.
Yeah, yeah, and again, I mean, you compute those vertices automatically by computing the convex color, but
Right.
would it be useful to give the user the freedom
To relocate
for
them?
everyone?
Yeah. That's a previous paper of ours. We let the user relocate them. And we sort of solve in real time for the updated weights as you do that. So if you ask me, I can show you a live demo of that. Yeah.
So, having done this, you now have this non-identity curve for luminance. Subsequent edits aren't going to perform the same way that edits on the initial image did, because that purple curve might run into, the upper bound at 1 sooner. So you could take this image and restart from there, or you can continue editing. What are the advantages and disadvantages?
Yeah, great question. So we do have like a bake button, right? Which like bakes this in and sort of resets, right? Exactly, so that you don't kind of run into that kind of issue. I personally, I love the sort of push pins, right? I mean, going all the way back to, as rigid as possible shape editing, right? You have push pins and you can add and remove a pin at any time and things will snap back, right? So it makes your edits commutative, which I think is like nice, right? It's like, my edits are commutative. I don't need to be so concerned about like which order I've done them in. I know that the fact that they exist in this way gives me this result. And if I like change any of them, remove any of them, I'm getting the same thing no matter how I got there. I think that's cool. I think that's a nice feature. And so I think it's like trading that commutativity versus, you know, not things getting like over constrained. So we also did an expert study where we, you know, go and get 10 experts with an average of, you know, some of them had 30 years of experience, some had 3 years of experience. You know, we get them to use it. We you know, give them a scenario, like change, like make some edits, play with it, do some freeform things, get some Likert scale data, ask them how much they like it, and you know, they like it. A lot of blue there. You know, and like to sort of summarize a lot of the feedback, right? They really don't like making masks. Like the masks really are tedious, right? So you know, like the results, like yeah, they look good, they look fine. I mean, they look good. I don't want to like undersell how good they look. They were happy with it. It looks good. Like you can get good results in Photoshop too, though, right? Like, and so that was sort of a key thing, right? Was that like without doing a lot of tedious masking, you get really, you know, nice looking results that they're very happy with. This is some fun edits. You could do this as like a different way to grayscale an image. So take the image, do this to it, then take your palette and set the palette, you know, to 0, right? So now all the colors are gray with, and you can manipulate the like tone, the like lightness curves for different portions of the image, you know, separately, according to like what colors they had in the input. And then you could also use this to sort of.
So you could make the brick lighter.
Exactly. Yeah, exactly. And then here, you know, selectively bring back a little bit of color. And then here's an example where it's like you took an automatic, you know, depth estimation algorithm and then said, all right, you've got a, you know, 2 palette image with depth as the weight's coming from the depth values. And now you can like edit the like tonality here in depth according to depth. So the foreground stays, you know, bright and the background's gotten dark. Okay, so for this portion of the talk, you know, what we did, we united this palette-based and palette-based editing with tone current editing to give us like color-aware luminance controls. We also, you know, figured out a way to do this sparse to do real-time like constraint-driven editing on pixels, so image space edits as well in a sparse way. It's not semantic. You know, there's no semantics here, right? It's only about the colors in the image. So there's like a lot of great work happening, you know, on, I don't know, like in the computer vision world on semantics and object recognition and so on. And like, we're using none of it. So that's like, seems like a potential there to do something with that. Also, you know, videos, did have a collaboration at one point where we were doing, some of this palette-based editing on videos, right? But this work has taken palette-based editing in a different direction, and you know, to kind of see how that would work on videos. Text-guided editing is a popular thing these days, right? So how can, you know, text-guided editing interface with this? And then of course the gamut itself, you know, you can end up running into the gamut, and there's all work about compressing colors or based on gamuts, and to keep big things from going out of gamut, that would be worth doing. You can download it. You can go and download it, and you know, thank you to the photographers who participated. And yeah, great. Shape. I promised more than color, so I will move on to shape. Great. So this is work by Jialin Huang. Did I mention there's like a little lag here? So I see here again. Yeah. On the one hand, it's good because I know what's coming before you.
Are you supposed to?
Yeah. And our collaborators, Monica and Alexis. Okay, so the question that drove this work is how can we create a non-visual interface for shape perception, right? Computer graphics is wonderful. I love computer graphics, but we very heavily rely on visual. Our visual perception to perceive graphics. It's almost in the word, right? Graphics, right? But anyway, there's like lots of great applications of computer graphics, right? We can create and edit shapes. We can interact with them. We usually see them on screens, and maybe we see them in VR or spatial computing headsets. Okay, so this is shape sun, and it's all sonification, which I'll talk about. It's a approach for perceiving shapes, where when you use it, you don't actually see it. You see nothing. You see nothing. Okay, and so what is sonification? So sonification is mapping information to sound, right? And here's an example of sonification. All right, so that's like, for continuous data, it's, people have used it for like 1D data like this in the past. We want to use it for 3D data, right? I guess I should say, like, did we consider other things, right? So we're ruling out visual perception. There's also, taste, smell, sound, and touch, right? Touch is sort of the obvious one. I love touch, but like, when you look at the state of, haptics, they're not very accessible or available, right? Like there are some really awesome, like you see in the literature, like exoskeletons, right? Your hand goes in, and so you can try to touch something that's not there, or the phantom pens, right, which give you this 1 degree of freedom, which is much more limited than how we usually touch shapes in the real world. But some of these touch devices exist. They're awesome. If there was like an exoskeleton that cost like $400 and gave you full pressure and resistance, I probably wouldn't be doing this research. But those things are very unavailable, right? And yet, like, hand tracking is quite available. All you need is the VR headsets are doing it these days, but like really, you don't even need a VR headset, right? You just need to do what we're doing. We just need headphones and hand tracking. Great. So it's it's about availability, and it's just an interesting problem. So how should we map the hands to sounds, right? We can consider fingertips. We considered kind of things with the whole hand, looking at the curvature of your hand. How your hand is curved. For this work, we settled on fingertips. It's you don't have to think about how your hands are colliding, and you're usually aware of our fingertips. And then, of course, there's like many different ways to map data with sonification to sound information, right? Volume, pitch, timbre, spatialization, tempo, other features of sounds. What we found, or what we focused on, was volume, pitch, timbre, and spatialization. So I'll kind of walk you through. This is a very design-heavy project, so I'll kind of walk you through the design and what we end up with. So in our sonification, we sonified regions that divide space around the shape into different zones. So first we've got, outside the shape, right? If your hands are outside the shape, you don't know where the shape is, you're looking for the shape. Inside the shape, so once you're contacting the shape, when you do that, in the physical world, if I physically contact the shape, there's like an abrupt, discontinuity in what my fingertips are feeling, more or less. So that's different. And then, maybe there are features that are worth like knowing about. If something is like an edge, it's kind of sharp in one dimension. And if it's a corner, it's sharp in all dimensions. Great. Then there's, spatialization, right? So we did not end with 3D simulation of like where the sound is in space and how it's hitting their ears. Humans are not very good at distance estimation. We're okay, like less than 10 degree accuracy, a little less than 10 degree accuracy for if we hear a sound, knowing like which direction it's coming from. We're not very good at knowing how far away it came from. Like, is it a loud sound that's far away or a quieter sound that's closer? And in particular, yeah.
I can swat a mosquito. when I'm asleep, when I'm lying in bed. at
Yeah,
night.
yeah.
Nailed the sucker. That seems like pretty good localization.
Yeah, I
Like,
mean,
I'm not swatting mosquito 10 feet away.
maybe it's because we know that like we know the volume of the mosquito, so like knowing like it's a mosquito this loud, that means that this, yeah, maybe we're a lot
Maybe
more
you need
accurate.
to use mosquitoes.
Yeah.
There's something you know the volume.
You did interact with more mosquitoes.
Yeah, yeah. The shape is made of mosquitoes.
Really pleasant user experience.
In terms of, in terms of the, like, your fingertips could be close together if you're touching a shape, right? So that like 10 degrees of accuracy is like also like, we're on the threshold here. So we ended up doing whatever your right hand's doing goes to your right ear, whatever your left hand's doing goes to your left ear. And there's like a pitch difference between stuff in that your right hand does and your left hand does. And then, just to break these down one by one, so for outside, when you're outside the shape, you don't know where it is, and we want to kind of guide you to that shape. So it's sort of like about guiding you based on distance. Right, so it's volume, these are volume mapping there. And then, when you touch the shape, right, your fingertips are inside the shape, infinitesimally or more than infinitesimally, right? So, we pick contact sounds. And a different one for each fingertip on a pentatonic scale, which like generally sounds pretty nice for combinations rather than like very like disharmonic, right? So, if you get good at this, you can tell like which finger is contacting. And even if you don't know exactly which finger, because you haven't memorized this mapping, you can still tell that like a different finger is, starting to contact or stopping contact. So it's, it's useful for like, you found the surface and you're moving your fingertips, and now you can kind of do some of that interaction with your fingertips and the sound you're hearing to, get some curvature out of it. Yeah, and then we used ear cons, which are like icons, audio icons for edges, sort of like and for corner sounds like Okay, so how do we, implement this? We used a VR headset because despite there being like awesome hand tracking, GitHub pages which link to just like tons of awesome hand tracking research. A lot of it's just like I want to download it and run it, and it's like it's not in the same commercialized state, I guess. It's not in the same usable state, off-the-shelf usable state. There's like the Quest, right? So the Quest hand tracking is pretty good. The latency's not awesome, but it's good enough. And it really just works out of the box. So we did that. And then we use sign distance field, right? Take whatever shape you want, give sign distance field, and now you have immediate lookup for the distances, which is all we need.
Well, you also need the corner and edge detection as well, right?
Yeah, right. So we can, do just, those features, I think if I remember right, we just computed those on the fly, right? Set of points and lines and just move those on the fly.
So the Stanford bunny is typically polygonal, right?
Yeah.
So between any two polygons, there's an edge.
Yes.
That seems like a lot of edges. So you must have some threshold.
Yes, we have a threshold. And, we used automatic edge detection with some, angled, dihedral angled edge threshold. And then if we didn't like the output, we would also just clean it up, right? Like this paper wasn't so much about the pipeline, but like all of that working as it was like, can we do this? Like, can people actually perceive a shape, without any visual feedback? So we're okay to, do a little bit of bam, Yeah.
So just wondering, so it seems, for each different finger, the user will get a different sound. So what if they have point two fingers on the, same, like on the same, on the surface? Cause it seems, there are a lot of combinations. So do the users need to remember each, each different, output for each combination of the
Right. So if so if you're reaching your hand out and your index finger makes contact, right, you're gonna hear, what did I put up there? C, D, G.
Yeah.
Yeah, okay. So, you'll hear that. And then, when your second finger makes contact, you're gonna hear a different pitch, like a second pitch added on, right? So you'll hear a chord, right? And, you don't have to memorize, which finger is, most people don't have absolute pitch, right? Although we have relative pitch. So, we don't have to memorize that, right? To like, you're moving your finger, right? There's this like embodied action where you've moved a finger and now you hear something, right? So you can get the sense of like, this finger just made contact, where before it wasn't making contact. I don't know if that's answering your question.
There are a lot of people with what I would call sound blindness. It turns out you can play a C and a D and ask, are they the same note? And like 12% of people say, yep, same note. C and F sharp, yeah, they are the same note. So.
Yeah. I mean, I guess, they wouldn't be very good at knowing which, like, the different fingers had suddenly made contact or not, right? But like, to me, that the discontinuity of the sensation of touching something, going from not touching to touching.
Is the key thing, yeah.
Yeah, that's the key thing,
It's gotta be 90% of the.
Yeah. Exactly. So we did this, we did an experiment, and we brought in, 15 sighted people, 6 people with who are, BVI, blind or visually impaired individuals, and we had them use this. And we did, 2 kinds of tests. One was like shape recognition from a set. I'll show you that. And the other one was like landmark localization, which is sort of like, I don't know, I didn't expect it to work as well as it did. Shape recognition was like, okay, here are some sets of shapes. Got 3 sets of shapes, some simple ones, some medium ones, slightly more complicated ones, but nothing too complex. And they're in these groups, and we tell them, it is either a cone, a cube, or a sphere. Can you identify it, right? Like, if we can't do this, then we probably can't do anything. But we could do it, right? So Shape Sonic users had an 82% success rate. If you were guessing randomly, you have a 33% success rate. So like, that worked. And sighted users and BVI users had similar performance. That's interesting. So onto the harder task, landmark localization. So in this task, there's a shape, a pyramid, a simple shape, or a cat, which is, pretty complicated. And the way this task worked was we first described the shape. We said, okay, there's a pyramid in front of you. Go ahead and touch where you think the top point is. And you don't really know where the top point could be. This is without Shape Sonic, right? So first we're doing it without Shape Sonic, just like given only a verbal description, how well do you do, right? And they touch where they think the top point will be, and then touch any corner, and then like touch the bottom, right? And then we rerun it and then we give them a few minutes to use Shape Sonic on the shape, so they're kind of feeling around, getting a sense for where things are, and then we tell them to touch the top point again, and then it's like redoing that. So it's sort of like proprioceptive memory, because we didn't want to give them like a long time to like explore, but just like, now that you have a sense for the shape, touch that top point. And so the smaller circle is with Shape Sonic, and the same thing with the cat, right? Smaller circle is with Shape Sonic, larger circle is without. The cat was second always, so maybe we just got a lot better at using it because the ratio difference is much larger for the cat. But the cat worked a lot better than I thought it would. I mean, it's not a simple shape, right? But like touching a paw or a tail or an ear, right? Were the task, right? Like if I tell you there's a cat in front of you and it's approximately this big, and then you say like touch where you think the ears are, like people aren't very accurate at that. Touch where you think the tail is, and then we got it.
And just to clarify on
Yeah.
the thing you're actually measuring here is they've had time to sort of a brief amount of time to play with it. And then you tell them just to reach out and like just instantaneous touch one point, and that's all they get to do.
Yeah. I mean, we weren't like, there wasn't like a buzzer if it wasn't instantaneous, but it was like just reach out and try to touch where you thought it was.
So they don't really get to like reach out and feel along the shape again to find it. They have to sort of remember where they think it was.
Right, exactly. That was the intention. And they had like 5 minutes of actually free exploration, and then when it was like reach out and touch it, I don't think we, I think we told them to do it quickly. I don't think we like, gave them a hard cutoff, but it was like, few seconds.
Gotcha.
Yeah. Yeah,
So,
yeah.
sorry, is the large circles, that's random guessing or?
That's with only a verbal description.
Verbal
So,
description.
yeah, I mean, random guessing. Yeah, you're right to call it that.
I did want to know in the cat situation where user was given the instruction to touch the tail anywhere or like a specific middle point.
Yeah, I think it was anywhere on the tail. I think it was anywhere on the tail.
So when you show the error map here, it's just sort of like,
We just put it
Okay.
somewhere.
but it's not like with respect to that point.
No,
Yeah.
no. And the pyramid was like anywhere on the bottom, you know, top point. Top point is so, maybe that's because it's the first, you know.
The Bayesian in me looks at this and sees the difference between prior and posterior distributions. Someone's like, oh, what's my prior distribution of where a cat's tail is, right? And then it's like, now I've actually gotten to see the evidence. Now where is it, right? Yeah.
Thanks. Yeah. And let's see, there's some other observations that, I don't see my presenter notes now, but, see if so there were, I think, 3 people who had like, they were like, 3 BVI people who were like extremely good and were like nowhere near their skill ceiling and just seemed to have like an uncanny ability to like really follow the surface and, remember the sounds very, very well. That's, I hope I reproduced that right. Jelen would have done a better job. So we also kind of asked like a kind of overall question, which is like, place this experience on a continuum between someone telling you about a shape or like feeling a shape physically, right? And like where is shape sonic, right? And it's like, halfway between, right? And which degree do you perceive the sensation of 3D shape? And it's like, halfway between. So I think that's a win. I mean, like, there's no way we're gonna give someone the sensation of physically touching a shape without tactile feedback. Like that was not in the cards. So I'll take halfway. I'm very happy with that. Yeah. Yeah, and we definitely haven't, reached the skill ceiling for what people were capable of, right? They trained for a little bit of, doing this, but not an insane amount of time. And then that tracking latency, I wish it were shorter. It's much longer than like what you get with the controllers. Yeah, obviously there are like other things to do in the future, other physical attributes like the materials or doing like a, physical simulation, of the resonance of the shape when you hit it, knowing what material it's made of. Doing more complex objects, yeah.
There's also a prior on shapes, right? All your subjects knew what a cat was.
Right.
If you said, here's a random shape,
Right.
I want you to, identify the top point, and it's, an overlay of a cactus and a Subaru.
Right.
That becomes a real challenge.
Right, absolutely. Yeah, I mean, that was sort of like, right. Like yes, yeah.
I'm imagining this now sitting on campus where Blue Note used to be, the Subaru cactus.
And in cognitive science, they'll do that, like kind of visual perception, right? On these like abstract shapes and yeah. I mean, that's interesting. I think like for this like initial work, it seemed to be kind of straying too far from like a sort of somewhat realistic scenario you might hope to put this in, was like, of course someone could tell you it's this, but that's not the same as like the vivid sensation of a physical object in front of you, right? And it was like, okay, how close can we get?
Did the BVI individuals have suggestions or reactions to how you mapped things to sounds?
Yeah, so some of them were familiar with like sonification, but a lot of them like weren't familiar with, sonification at all. In like some pilot studies, one interesting feedback was that like they were definitely more tolerant of sounds than we thought they would be. Some of the sounds I thought like, I think in one of those early versions, the sounds were like pretty unpleasant, but it wasn't like, it was like, how unpleasant is this? And it was like, yeah, it's fine, and we're like, oh, okay, like, I thought it would be, I didn't think it would be, I thought it was like much more pleasant than it was. And Jelen would probably be able to give you a better answer. Or I can give you a better answer by checking some notes later. And so that's Shape Sonic. You can actually download some APKs for Quest, so you can do that. And I will very briefly talk about thought. I have like 10 more minutes. Is that right?
Yeah.
Okay. All right. So let's talk about thought. Talk about color and shape. Let's talk about thought. And I do have a somewhat specific meaning of thought here. And it's it's about scientific communication and, I'll focus on like graphics communication and maybe linear algebra, right? So this is work, this is Yang Lee's work, he's on the job market, and, this is kind of gonna briefly go over like 2 different papers and self collaboration. Right, so the idea here, is that, you know, someone who's going to do some, interact with the scientific literature will, you know, find a paper, they'll find a paper, they'll open it up, they'll find an equation, they'll look at that equation, they'll go, okay, I wanna try this, so they'll implement it, right? Maybe they're working in C++, so they'll open their, you know, C++ editor, they'll type it in, they might make a mistake. And the mistakes can be kind of subtle, like, you know, the I should be a J here, right? And like, that's annoying and to find, right? And at the same time, someone else might be like, well, I'm working in Python, you know, or JavaScript, and so they'll re-implement it, right? And that seems like wasteful, right? And then there's all these like, you know, these symbols don't really, like, they kind of look like math, but like, not really. So this like redundancy and ease of introducing errors is, you know, something that seems wasteful. And at the same time, people who write papers sometimes put in typos in the papers as well, right? And then you're going and you're implementing this and you're
I
like,
don't know what you're talking about.
yeah, never happened, right? So the kind of like, what if we could do something which was basically like a compilable, like a markdown, like pretty pleasant to type, but it compiles, unambiguous execution of math, right? Like all math, definitely no, it's not even meant to be executed, but like some math formulas are written as like formulas to be executed. And so that's the goal here, right? So you can write something that's like looks, you know, as mathish as we thought we could make it, while sticking with like Unicode without going into the wild world of Unicode. And when you do this, you get to run this through a compiler, and the compiler will give you, you know, will go through LaTeX and typeset it nicely. But it will, the same compiler can also give you a C++, Python, MATLAB, whatever backend you write for it. And so now you've written one thing and you get, you know, all these different forms. And so just to kind of like put this on a plot, right? Like going between like conventional linear algebra syntax, like does it look like linear algebra or does it like look like C++ or APL? You know, that's the x-axis. And then like the y-axis would be like unambiguous execution, right? So LaTeX, you can't execute your LaTeX. It's not unambiguous. You know, ASCII math is, you know, similarly. Programming languages, you can unambiguously execute them, but like, you know, they're more to the left. And so our goal was to try to get as far to the top right as we could. Cool. So, you know, how do we go about doing this, right? Like what kind of math should we cover? So let's, you know, so we went to SIGGRAPH, looked at all this papers from SIGGRAPH 2019, collected like 2,000 equations, almost 2,000 equations from SIGGRAPH 2019, and just kind of tabulated, like we, you know, we tabulated different things that appear in these formulas and decided which ones were like a reasonable thing we could cover, right? So.
Did you account for typos?
Yeah. We did not account. So single letter variables, like almost universally done, right? Almost universally done single letter variables. I'm not even gonna put up here like juxtaposition is multiplication, but that's like, that's what's done in math, right? And very few programming languages have done it. Fortress did it, but very few programming languages did it. Julia does it with like a numerical, like a literal in front of a variable. Externally defined functions, yeah, those appear, but like summations, various norms, some minimization, trigonometric functions, integrals, like these things appear. So let's tackle these in, you know, most important, least important order. I will not give a live demo at the moment, in the interest of time. But it runs in the browser. This thing runs in the browser, so you can go in there, you can type in formulas, and you can hit the compile button and get like, you know, see the LaTeX version or copy the LaTeX source or the C++, you know, Python and MATLAB. And, you know, copy code as URL, and like that URL will take you back here with the thing filled in. So I encourage you to play with it. Oops. No, I just said I wouldn't click on it. But this like seems like a good foundation for papers of the future, right? Like what if we were using IRLA instead of LaTeX in the papers where it was appropriate, right? So that was this sort of second piece of work here, right? What if you could have a paper that compiles to a library for improved replicability and interactivity? And then like, what else could you do with all the metadata that you get from having, you know, compilable, from having, you know, this compilability of these formulas, right? So we can improve the readability of papers. So that's like, that was the goal here with Heartdown, right? So Heartdown, like Markdown, where you can put in, I heard of like code blocks. And then out of this, you get, you know, this like authoring environment where you know, you get the paper, but you also get like a glossary for free. You can go and you can click on a formula and see like where those things were defined or described in the paper. And then because we can execute, you know, the formula, then, oh yeah, we'll also get like compiler errors, like, hey, you didn't describe D. Like, you used it in your formula, but you didn't describe it. And then, you know, you get figures that you can, you know, interact with, and you can go and you can say like, let me just change this, let me like square this Laplacian or cube, let me, you know, just try a triharmonic function, and then like it updates and the figure updates. Yes.
So in your examples, things keep being in domains that are either R or Z. Am I restricted to sets that are of types that come from programming languages? Like, for the spline, I really want T to be between 0 and 1.
Yeah. We, future work.
Fair work. Okay, great.
I did have a student who did, he did,
I asked my PL friends this question,
Yeah,
too, like,
yeah.
why can't you give me a type that is the unit interval? They're like, shut up.
yeah, so I had a master's student who did like an iHeart IQ, like an ego Keyless, like, you know, like shader code thing, where you give your sign distance functions in like, you know, iHeart LA, and then he added types for like colors that would kind of, because he wanted to automatically create sliders for things. So he had range syntax, so it would choose the range of the slider or interact with. Yeah. So, you know, the design goals here, let people author, read, and make use of or experiment with things. And, you know, we want correct and reproducible documents with minimal authoring overhead. And we also wanted ecological compatibility, meaning like, you know, the ecology that we live in. Like, we like to edit, you know, in text documents, right? We don't want to change what authors put in papers or how they do it, right? So plain text documents where you can put in prose, math, figures, and tables. And, you know, what better way to do it than to do a formative study, look at hundreds of cigarette papers, realize that prose organize the document. So it's like the math can appear out of order in a paper. So looking at this example, it's like, here's a formula, but where are the symbols defined? And it's like, oh, they're actually defined later in the paper. And even a symbol in that later thing is defined later in the paper. And then it's like described in prose, you know, which could come after it. So definitely can't assume things appear in order. But, you know, putting all this together, symbols can get reused in different contexts. We did this formative study. We in the interest of time, I'm gonna not go into all these, things, but like the same symbol can be reused in different sections of the paper. There are derivations, right, which appear using symbols, as, you know, the same symbols, and like it'd be nice to track that, right? Even when they're not like formulas that can be executed. And there's like additional kind of functions are used a lot. We didn't really do functions in iHeart LA, but we extended iHeart LA for this later work to add, you know, functions. Boom, there's a bunch of functions. And what should we support? Let's look at, you know, what people do when they make functions and, you know, support those things. So there's the context. You kind of say like context, you can reuse symbols, which compiles in a different like library. We use, you know, span tag to say this is a definition, but we automatically figure out which symbol's in there. Say, sorry, a description, what symbol's in there. There's the code block. And figures, you know, a block of like Python that can use the library. The video already kind of highlighted these things. So you forgot to describe this symbol. We'll get a, you know, you get the glossary for free. And as you scroll, the glossary will like switch to the glossary for the appropriate section. Cool. And, you know, here's like a formula, and you can click on a symbol, and, you know, it'll tell you like, this is where that symbol was described. right? Or you can click on like the whole equation. And it will show you, it'll pop up like where all the symbols, like where that formula is used and where all the symbols come from that are used in it. Cool, and I basically already showed this, a demo like this. This is a similar demo with like clustering, but I'm just gonna skip this because I'm close to the end. And I am close to the end because the next slide is the conclusion. So conclusions, right? So I think there's a big potential here to benefit the scientific ecosystem. Like we focus on graphics and specific kinds of graphics papers in a sense. But in theory, other people can benefit from this. We want to make it easy to try new ideas, right? And like avoid the replicability crisis, from other fields. And there's this idea of like translation loss, which is like, you describe an idea, and then you go and you formalize it. Somebody hears it, and they go and they formalize it. They write it down. When they write it down, then someone else is going to go and they're going to read it. And once they read it, they're going to maybe go and implement it. And when they implement it, they might implement a bug, right? So each of these steps has like the possibility for error, right? And that's what we're trying to minimize. So again, you can try it, you can download it, and so on. And this brings me to the very end. So I talked about color, shape, and thought. And thank you for listening.
We're technically over time, but if folks want to stick around and ask questions, you're welcome to do so.
I want to ask you, do you remember Slidey? There's this Slidey. Is this a thing that let you make animated PowerPoint slides? Beautiful talk on font resize, rescaling that had everything. And it was released as a library and people have used it. And at some point, my student Morgan said to the students, never ever give me something produced in Slidey again, because when I try to run it, fail, etc. It takes a lot to make a new tool work.
Yes, yes.
I mean, this clearly produced better presentations.
Yes.
And people stayed away in droves.
Yeah, it's
What's your plan for adoption?
Yeah. I mean, one thing that's nice is that like the output, the output can just exist, right? Like it's putting out LaTeX. So if like, so there's I think I'm answering a slightly different question about like what if it stops running? What if the software stops running in the future? That's a different question, which what's our fit for adoption? I don't know. We sometimes talk about what we need to do to take over the world, and it's like run a browser, cover more things, give people more benefits, automatically invert papers into it,
I think it feels like it's a socio-technical problem. So it's not just what cool features you built, but like how many people you can convince to become passionate advocates for it. And you've got, really prominent people in the field who are advocating for it, you and Alec. And so it sort of seems like how do you recruit others to sort of be as passionate as you are about it,
Yeah.
Others who have probably been writing the LaTeX for their papers for, however long
Exactly.
the field has been.
Yeah, I mean, I think it's
There's a big case to be made for getting the youngest people you can
That's a good point.
to do it. This changed radiology.
Infect the new generation.
Radiologists,
Yeah.
like old radiologists only wanted to see X-rays, and young radiologists said, we've got data here, we could look at things in 3D. And at some point, the old guy said, that person is seeing things that I wasn't able to see. Maybe I should learn this.
interesting.
The Python developer, right?
Yeah.
Big Python.
Yeah.
I'll just force all my class, the students in my class.
There you go. You can only do your homework in this.
We sometimes talk about the pedagogical, if a advanced graphics class or even a graphics class, like implementing formulas, what happens when you can just hit compile? Like what is the pedagogy, like what are why should I be typing this in C++, when the compiler can do it for me?
I think we had this argument in the 1960s. You know, is automatic compilation bad for computer science?
Yeah, right.
I
So make them, I should make them lazy, right? Yeah.
Right after.
If you don't know how to patch machine code, you're not a computer
Yeah.
scientist.
Well, yeah, great. Great.
I bet you that was 30 years before you were born.
Yeah. There's always that.
Okay, great to see you.
Should I stop sharing?
I think we're basically done.
I think we're done.